Okay, this will be the first in our series of lecture notes videos. I'm working on updating the equipment and formatting, so these might change and develop as we go along, but for right now, we will try this arrangement. So we're going to start with talking about angles. Most of us have a fairly intuitive idea of what angles are. Our goal here is less, learning angles as if we don't know what they are, and more about building up a set of kind of common vocabulary so we're all using the same terminology, so nothing comes as a surprise. So first, if we want to talk about an angle, we're certainly talking about rays, and rays are lines coming from some initial point out in a particular direction. And if we have another ray coming out that shares a common vertex, then that forms an angle. Now, this angle that we're looking at here isn't really unique until unless we label it, because our angle, we might think of by default as it being measured from this side to this side, where we call the side in which we start our initial side or initial ray, and the side our angle stops at as our terminal side. Now, this angle that we're referencing here is different, for example, from that angle. They both have an initial side and a terminal side in the same location, but they are different behaviors. One's turning clockwise, the other's turning counterclockwise. One's smaller, would be an acute angle, the other's a large angle. Similarly, if we could go through a third angle, say one that's going all the way around and then stopping there. All those angles, the three there, have the same initial side and the same terminal side, but they are different angles. If the angles are propagating at a particular rate, they take different amounts of time, different amounts of energy. They are fundamentally different angles. And one of the things we're going to do to try to kind of help that and help specify that is we're going to have a tendency, let's see if I can make this grab. I can't, that's okay. To put our angles in what we're going to call standard position. And to put an angle in standard position, we're going to use a Cartesian coordinate system, our good old XY plane. And we're going to place our initial side along the positive x-axis. That's the fundamental nature of an angle in standard form. And when we track out an angle, or when we swing around some angle, our angles are going to be measured positively if they go in the counterclockwise direction, and we're going to consider them to be a negative angle if they go in the clockwise direction. And yes, we do have negative angles, positive and negative angles. If you track through an angle of 20 degrees and then track through an angle of negative 20 degrees, you're back where you started. So we might have some angle here at, that looks like somewhere around, I'm going to say 42 degrees. We'll talk about degrees more in a minute. Where we might have an angle down here, say this angle. I'm not putting it as a dotted line for any particular reason, just to kind of highlight the negative ones special for right now. And that one might be, I don't know, say negative 30 degrees. Yeah, looks a little more than that, but that's okay. And similarly, we can have angles that go all the way around through a full rotation and then a little more. That would be a full, in degrees, 360 degrees plus a little bit more, so it would be 360 degrees plus a little 42 degrees. So how about 402 degrees? So this would also be able to be the terminal side of a 402 degree angle. And while the 42 degree angle and the 402 degree angle are different angles, because they share that terminal side, we tend to refer to them as coterminal angles. Which really is just what it sounds like. Two angles that terminate at the same corresponding location. They are coterminal. For many of our tools, coterminal angles will behave similarly, so it's handy to know this. But keep in mind that a movement of 402 degrees and a movement of 42 degrees are certainly different movements. They're different angles. But they are similar in important ways, and coterminal is the word we use to reference that. So one of the things you'll do early in these notes that we have to go through is, represent angles in standard position. And the main thing is to make sure you have a Cartesian coordinate system. You should really be labeling your X and your Y, just out of good habits. You can put a scale on it. I've got a scale here of 1, 2, 3. Scale isn't terribly necessary on that, but it's a good habit to, whenever you draw a graph, draw a scale on it. And make sure your positive angles are going in positive directions. Your negatives are being measured in negative directions. I think you're asked for 170 degrees. We know 180 degrees is a straight line. So, yeah, that's a little steep. So 170 degrees, I don't know, might be about there. And you could get a protractor and measure it out all nicely. I'm not really asking for that. I'm more asking us to have a good idea, kind of an intuitive sense of what and where some of our angles are. If we're asked for a negative 60 degree angle, negative 60 degrees. That pen's a little fat, sorry about that. But I like the color. So if those give you any trouble, let me know. I think there's one that's more than one rotation. So if we had, say, it could even be somebody wants to draw 1,000 degree angle. Well, we know 360 degrees is one full rotation, so it would take, two of those would be 720, so it's going to take a little more than two, so it's 2 and another 280 degrees. So it would be coterminal to 280 degrees. 1,000 degrees and 280 degrees are coterminal. You can always create a coterminal angle by either adding or subtracting a full rotation worth of angle. Now, do notice I said full rotation, not 360 degrees. 360 degrees is a full rotation in degree measure, but we will talk about other ways to measure degrees. So from whatever measure you have, you add or subtract a full rotation and you'll get a coterminal angle. So if we wanted to draw that, it would be nice for us to remember that, again, our initial side is at that positive x-axis. We'd be going around twice, so one time around, two times around, and then 280 is 90, 180, 270, so 280 would be about there. I certainly wouldn't draw those all on the same graph if I were you. It does make a bit of a mess. So be sure to space those out nicely. Now, I did mention that we will be talking about other ways of measuring angles. And the reason we want that isn't because degrees are bad. We use degrees a lot, and a lot of people use degrees for a lot of applications. The problem with degrees is that they fundamentally don't mean anything structurally. We have 360 degrees in a full circle because someone picked that number a long time ago. There's a lot of math history debates about exactly where it comes from and why and who started it. Some say the Aztecs, some say the Greeks, some say, But either way, 360 is the number of pieces we cut a circle into it because 360 is such a handy number. You can divide it by 2, 3, 4, 5, 6, 8, 9, 10, 12 without getting decimals or fractions. And that's really handy, particularly in an early system of measure. But again, the problem is it doesn't have any structural meaning, so it's kind of hard to work with in certain types of applications. So it would be nice for us to have a system of measure that has a little bit more of a structural meaning. And to do that, we're going to look at, some of the other ways in which we use and care about angles, and look at what kind of structural meaning. Oh, that circle's behind there. I can fix that, I think. Yeah, not going to worry about it. I'll just draw a circle. So, one of the things about angles, because angles go through a rotation, is we do associate angles with circles pretty dramatically. That's a terrible circle, but that's okay, you'll forgive me. So when we talk about wanting to measure angles, it is really handy to consider what's happening to that angle and the circle it might be going through. That's a little bit better. I know, I was going to deal with it, but I couldn't. Yeah. Still, we'll call that a circle. So some of the things that you might care about when you're drawing a circle are things like, dealing with a circle, are what its radius is. Okay, we know the radius should be that distance from the center out to the edge, and that's going to be the same distance here, the radius of that circle. The trouble is, relating the radius of a circle to its arc can be fairly difficult. We know it runs into some troubles. That's one of the reasons we have our best friend, the irrational number pi, is because that that relationship's got some issues. So if we want a nice tool to relate the angle of a ray and a circle, relating it through that radius might be nice. And one of the kind of more straightforward ways to do that is to make our unit equal to the amount of angle necessary for this angle to create an arc that is the same length as the radius of our circle. Now, whether I've drawn that angle in just quite the right place, that's up to interpretation. It actually does look a little short, but that's okay. So, if this circle was radius, say, 5, then this length would be radius 5. It's the same radius. The amount of angle necessary to make this arc also 5. By the way, we often use S for arc length, so good time to get used to that. So I'm going to label that real quick. Arc length. Just see. Pens are too fat. Arc length. The amount of angle necessary to make the arc length of the circle, it's called inscribed by the angle. We're going to call that 1 unit of measure, 1 radian. Abbreviate it RIE. So 1 radian is the amount of angle that scribes an arc of length equal to the radius of the circle. It's a little bit of an informal definition, but it's got the pieces we need. Now, the nice thing about this definition is the structural nature of it. The fact that it links arc lengths of the circle, structural parts of the circle, to another structural part of the circle, its radius. And that link and that connection is very helpful and very strong for a lot of nice applications. We will see a disadvantage in using radians as we go along, but that advantage is worth the trouble that radians are going to cause us. So let's try this again with another circle here. So if I have a circle, trust me, that's a circle, and it has radius r. Let's again assign this a radius, let's say radius 3. And if we draw an angle, try to be a little more accurate this time, such that that creates an arc length 3, then again that'll be 1 radian. But what if we made an angle that made this big arc length here 6 units? And we might say this is inches and inches, if you want, units. Well, this little one would be 1 radian. This would also make another 3 units, so it would be 1 radian. So this big angle here is indeed 2 radians. And we could keep doing that if we did it again. This angle, if this arc length here was 9, if this arc length here was 9 and this radius is still 3, then this big angle from there to there is 3 radians. I'm going to change that pen next time. And yes, of course, we could keep going. We could do another one. That would be, what, 4 radians? We could do another one. It's a little far. We could do another one at 5 radians. We could do another one, 6 radians. And we could keep going. But here's the trouble. If we look at this diagram, and I've tried to make this diagram fairly accurate. If we look at this diagram and try to put this on our Cartesian coordinate system, remember standard position, so that has to be the positive x-axis, we notice something kind of irritating. Notice this 1, 2, 3 radians, gosh, it's really close to that, negative side of the x-axis. It's really close to being a full rotation, but not quite. 6 radians, it doesn't go all the way around. 6 radians will always be a nice, perfect amount of the circle along its edge. That would be what? 3, 6, 9, 12, 15, so that would be 18 units. So this arc going all the way around. The handy thing about radians is there's no question. That's 6 radians. That means it's 6 radii. So that arc length is, hard to write in that arc length is 18. So the ability to make those kind of calculations quickly is really, really, really nice. The bad part is that notice how many radians we have don't fill the circle in a nice way. Like if we went to 7 radians, we'd be back up into this area, this positive x-axis, positive y-axis area. We have a name for that. We need a name for that. You remember your quadrants. That's your first quadrant, your second quadrant, your third quadrant, and your fourth quadrant. If it ever bugged you why the quadrants are labeled in that order, now you know why, because that's where we measure angles from. They start here on your positive x-axis and go through the first, second, third, and fourth quadrant in that order. So if we went to 7 radians, that would be back in quadrant 1, and it's not a nice whole number of radians to go all the way around the circle. Now that doesn't mean we can't talk about radians in whole numbers. We've been doing that. 1 radian is an amount of arc. 2 radians is an amount of angle, and it gives us a very, very nice arc length. But if we want to talk about, okay, how many radians are in one perfect rotation, I mean, by my diagram it looks a little more than 6, but if we wanted to know how many that is, well, we're going to have to do a little bit of geometry. So let me get all this stuff out of the way, and we'll talk about that geometry. So, back to a circle. I can make circles here. Make myself a nice circle. Yeah, you. That doesn't make the circle. Oh, okay, I'll use that one. So, if we have our nice little circle, my drawing tools. If we have our nice little circle, and we want to figure out how many radians are in a full rotation, going all the way around and back to where we started. Well, what do we know? Well, we know our circle will have some radius, r, and we want to know how many radians does it take to go all the way around. And remember, we said 1 radian, yeah, I like having the circle, 1 radian made this arc length s, 2 radians made this length s, and that s would be twice whatever the radius is, because it's 2 radians. And this actually sets something nice up for us. The radian measure here the radian measure, we're going to go Greek here, the Greek letter theta, which we often use for angles in degrees or in radians. So our angle there, theta, in radians is equal to the ratio between this arc length and the radius of the circle. So again, when this had a radius of 3, for 1 radian its arc length was 3. For 2 radians its arc length was 6. For 3 radians the arc length was 9. So that multiple of the radius is what defines our radian measure. So if we want a radian measure, really the ratio between the arc length it describes and the radius of the circle is really a good way to think of our definition for radian, sorry those look like J's, measure. I know we kind of define what 1 unit is over here, but a consequence of that definition of 1 unit, oh sorry that didn't quite make it on the screen, sorry. A consequence of that definition of 1 unit is that, I can even fix that. Oh, not quite right now. Is that in general our radian measure is this ratio. So if we wanted to figure out the radian measure of a full rotation, I'm going to write this as the radian measure of a full rotation, ROT. We'd want to be looking at the arc length of a full rotation. So arc length of a full rotation in ratio to the radius of our circle, whatever it happens to be. Well, arc length of a full rotation, we know what the arc length of a full rotation is because we know what to call that. The arc length of a full rotation is the circumference of our circle. So that circumference in ratio to our radius is going to be our angle measure of a full rotation in radians. And we know how to find circumference. Circumference is 2 pi r. 2 pi times the radius, or pi times diameter if you prefer, but the 2 pi r is handy. If we divide that by our radius to find that ratio, notice what happens to those radii. They cancel out. And we end up with the angle measure of a full rotation in radians being exactly a nice 2 pi. Now, 2 pi might not seem so nice. It is an irrational number. But we know kind of what it equals, because we know pi is, about 3.14, 15926535897. So we know twice that is going to be, well, not equal to, but about, so use little squiggly equal signs for about 6.28 and stuff. And that should correspond nicely to what we were drawing before. Remember, we had 3 radians about there, 4 radians about there, 5 radians about there, and 6 radians didn't quite get us all the way around. Sorry about that. Well, how many more radians did we need? Well, we needed about 0.28, 2 or 3 or anyway, radians to get all the way around. So, that 6 and that 6 really are the same 6, just we need the rest of that 2 pi to get all the way around. So what are we going to do with that? Well, because of that, it's common, not necessary, but common, to measure angles in radians in terms of what part of pi they are. Now, this is really important. We will often see radian measures be multiples or fractions of pi, but you don't need to have pi to be a radian measure. For example, if we had a, say, radius 7 circle, and we went through an angle theta of, say, 1.3 radians, and we wanted to find what this arc length was, well, we can do that. We know that the radian measure, theta, is defined really as the ratio between the arc length and the radius. Well, we don't know that arc length, but we can certainly solve this equation, S equals r theta, and you'll notice that in your reading, the arc length of a sector being the radius times the angle. But again, that angle has to be in radians because this tool comes from our definition of radians. But then that arc length is, well, our radius was 7. Let's even give it a measure again. 7 inches. And our angle was 1.3 radians. So how long's our arc length? Well, we can find this product. That product is what? 70 and 21, so 9.1. Now here's the fun part. Here's the best part. Maybe not the best part, but one of the best parts for radians. 9.1 watts. Well, this was measured in inches, so you'd expect this arc length to be measured in inches. But those of you who work with dimensions might be thinking, well, this is inches times radians, so isn't this 9.1 inch radians? What's an inch radian? I don't know what an inch radian is. Well, it's actually not, and the reason is radians are a unitless measure. We say radians, so we know what we're talking about, but if you look up here at our definition of radians, if this ratio is, say, arc length in inches and radius in inches, those units are going to cancel. Because radian measure is a ratio unit, it doesn't contaminate calculations. So we just get 9.1 inches. Now, if we had a, say, radius 5 circle and an angle of 40 degrees and tried to use this same tool and say it's, well, 5, let's say, feet times 40 degrees, feet, we would literally end up with 200 foot degrees and have no idea what a foot degree is. Degrees can't do this. But one of the nice things about radians is they do this. The radian measure doesn't contaminate calculations. So notice this entire problem happened with no pi's in it. And this is not a decimal approximation for something. This is exactly 1.3 radians. So don't let that throw you off, though it's an easy thing to have throw you off, that our radian measures do not have to have multiples or fractions of pi in them. But since that's the only way to get clean, even cuts of our circle, it's really common for us to have them. So let's look at how to do that. So if we want to find and start to get a sense of what some of our common angles look like in radians, we're going to start with the one thing we know. The radian measure, again theta, of a full rotation is 2 pi radians. So we know if we go all the way around from here at 0 all the way around, 0 radians all the way around, we know is 2 pi radians. Notice I'm not putting radians after it. As I said, radians, we don't need that radians there because it's a ratio. We often put it there for clarity, but we don't need it. Well, if it takes 2 pi radians to go all the way around, well, then how long does it take to go halfway around? Well, if that was 2 pi, then that should be 1 pi radians for half a circle. Well, then what's a quarter circle? Well, it's half of that, so pi over 2 radians. Well, if a quarter circle's pi over 2 radians, half a radian, then 3/4 of the way around, again keep in mind we're measuring positive in this direction, would be 1/2, 2 halves, which is the same as pi, and then 3 halves, so 3 pi over 2. Now again, keep in mind, is this still 90 degrees? Yes, this is a 90-degree angle. A 90-degree angle and a pi over 2 angle are equivalent. It's also nice to keep in mind, to remind yourself, that this pi over 2 radians is literally half of pi, so about 1.57 and stuff, where pi radians, it's about 3.1415926 radians. Remember in our other drawing, 3 stopped about here. Well, you need a little bit more to get all the way to halfway around the circle. This 2 pi, equivalently, it's about 6.28 and stuff. But we call it 2 pi because it's exactly 2 pi. We can keep going here too. If we take half of that, which we can associate with 45 degrees, that would be pi over 4 radians. That would make 1 pi over 4 radian to get here, another pi over 4 radian to get up to pi over 2. That would be 1 pi over 4, 2 pi over 4, which would reduce to pi over 2, then 3 pi over 4 radians, 4 pi over 4, and of course 4 pi over 4 would reduce to just pi, 5 pi over 4 radians, 6 pi over 4, which would reduce to 3 pi over 2, 7 pi over 4, 8 pi over 4, again 8 pi over 4s, 1, 2, 3, 4, 5, 6, 7, 8 pi over 4s, which of course again reduces to 2 pi. I'd like you to do this construction and the construction I'm about to do several times on your own, counting your way around the circles. We do really want to build up an intuitive sense of radians, like you have kind of an intuitive sense of degrees. It's going to help as we go along. Now, we could go from pi over 4s to pi over 8s, but pi over 8s don't end up being handy, so we're not going to. Instead of that, we're going to take this pi over 2 and break it into a third. So a third of a half would be pi over 6 radians. And then we're going to count our way around again. 1 pi over 6, 2 pi over 6, which would reduce to pi over 3. 3 pi over 6, which would reduce to pi over 2. 4 pi over 6, which would reduce to 2 pi over 3. Notice we skipped the pi over 4 because that's 1, 2, 3, 4, 5 would be down here. 5 pi over 6, which doesn't reduce, so we leave it. 6 pi over 6 reduces to pi. 7 pi over 6. 8 pi over 6, which reduces to 4 pi over 3. 5 pi over 6, again, we've got to move that same distance. Well, oh, lost my count. 6 pi over 6, 7 pi over 6, 8 pi over 6, sorry, and then that for 9 pi over 6, and again 9 pi over 6 reduces to 3 pi over 2, and then 10 pi over 6 would reduce to our 5 pi over 3, and then one more here, 11 pi over 6, which doesn't reduce, and then 12 pi over 6, which reduces to 2 pi. So we can build what our radian measures ought to look like just from knowing how much is in one full rotation. The fact that there are 2 pi radians in one full rotation can give us radian measures of lots of different cuts and breaks of the circle. So this is the disadvantage, I guess, with radians, is that if you want even cuts or multiples of full rotations, you have to be dealing with the irrational pi. But don't let that make you forget that if we want 1 radian is about there. That is 1. And ideally, we can even see that. You remember that pi over 3 that's there? What's pi over 3? It's 3.1415, blah, 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 over 3. Well, that should be about 1. And frankly, a little bit more than 1. A little bit more than 1. Well, where does pi over 3 land? A little bit more than 1 radian. So one of the first things that we're going to want to be able to do with these, because we're so familiar with degrees, it'll be nice for us to know how to move between the two, how to move from one to the other, to move from radians to degrees, or the other way. We're back. The nice thing is, particularly if you remember a little bit of dimensional analysis, it's fairly easy to do that. And to remind you of a little dimensional analysis, if we say had, I don't know, let's say 3 feet, and we want to convert that into inches. Well, I know, we just multiply by 12. We would just say multiply by 12. Okay, so let's make it a little harder. Let's say we had 10 inches and we wanted to convert that to centimeters. We can use the same process for either one, but this might be a little more motivating. So to do that, what we need is some connection between inches and centimeters. We have to know something about them. We have to know something like 1 centimeter is about 2.54. Wait, nope, sorry. That's backwards. 1 inch, sorry, is about equal to 2.54 centimeters. Knowing that relationship is what allows us to convert. And a good way to make sure your conversion happens in the right order, 110 inches, is to use your dimensional analysis tools. Use your conversion factors. So if we want to multiply this by something to change it from inches to centimeters, well, we're going to have to get the units of inches to cancel. So I need inches down here, so those will cancel. And I need centimeters up here. And I need to be multiplying by something that's not going to change the value. So the only thing we can not multiply by that doesn't change our value is 1. For a fraction to be 1, it has to have the same thing top and bottom, and not be 0. So we need the same measurements top and bottom, and we know that 2.54 centimeters and 1 inch are the same thing. So however much it doesn't look like it, this fraction really represents 1, which is why we can multiply it without changing anything. So if we take that product, we'll get, what, 25.4 centimeters after our inches cancel. So we're going to use that same idea to try to convert between degrees and radians. So if while we did this, you were unsure, well, that pi over 6 radians, how many degrees is that? Well, we can do that. Take our pi over 6 radians. Again, we don't have to write radians. If it helps with clarity, great, but we don't have to write it there. So take our pi over 6 radians and multiply by something that's going to get the radians to go away. So I want the radians in the denominator, so they'll cancel. Notice the pi isn't radians. The pi is just the number pi over 6, and this is radians. So I want those radians to cancel, and I'm going to introduce degrees. So all we need to know is a radian measure and a degree measure that are equal. Well, we could use that 360 degrees is the same as 2 pi radians. But it's actually more convenient to divide these by 2 and use 180 degrees and pi radians. It just makes the numbers a little bit smaller while still not having to approximate. So you could totally do this with 360 and 2 pi if you wanted to. Heck, you could do it with pi over 2 and 90 degrees if you really wanted to. But the 180 and pi, 180 degrees and pi radians, is really the handiest one in general. So we know that pi radians at 180 degrees are equal, so that's our conversion factor, just like our centimeters over inches. Our radians are going to cancel, and this is going to leave us an answer in degrees. That's what we wanted. Now, the nice part here is that those pi's cancel. Notice the pi's canceling and the radians canceling aren't the same thing. So, but those values of pi cancel, and we're just left with 180 over 6. Those even cancel nicely, and we're left with 30 degrees. So pi over 6 radians is equivalent to 30 degrees in measure. Similarly, you can go the other way if you wanted to know what, say, 120 degrees, let's start with nice ones, was in radian measure. We're going to do the same thing. We're going to want to get rid of degrees, so that's going to go on the bottom so they cancel, and introduce radians. Notice I didn't write pi, radians. And to do that, we need an amount of degrees, an amount of radians that we know are equal. So pi radians and 180 degrees are the same measure. That's going to make the degrees cancel and give us a unit of radians. And it's going to be 120 pi over 180 radians. And it would be nice to reduce this. They're both multiples of 60, so that's 2 pi over 3 radians, which should seem reasonable, but that's about 180 degrees right there. Oh, sorry, 120 degrees right there. Now, they can be uglier numbers. If somebody wants to turn, 124 degrees into radians, you certainly can. 124 degrees. Again, we're getting rid of degrees and putting in radians, so pi radians over 180 degrees. So 124 pi over 180 radians, the degrees have canceled, and then just reduce this as much as we can. 62 over 90, so 31/45 pi radians. What about radian measures without pi? Let's say we've got, 2 radians. And we want to convert that to degrees, because somebody wants to know. 2 radians, how many degrees is that? Notice again that radian measure doesn't have a pi in it. They don't always. It's not an even cut of the circle, but that's okay. You don't have to make even cuts of the circle. But then the process is exactly the same. 2 radians. We want to get rid of radians and put in degrees, so I need degrees on top, radians in the bottom, so 180 degrees over pi radians. Notice I'm sometimes writing radians and I'm sometimes not. As I said, that's okay, because radians is a ratio unit. It doesn't have a true value unit on it. But degrees does. Degrees is not a nice ratio unit. So if you're writing something in degree measure, it must have the degree symbol on it. If not, your angle was in radians. If I say I've got an angle of 45 and I leave that alone, that is an angle of 45 radians, because it doesn't say degrees. Be careful about that. Similarly, you can have an angle that's, say 5 pi degrees. That's okay. It's an irrational number of degrees. That happened. It's a little more than 16 degrees or something like that. So be careful. Don't let the existence of the pi or the lack of pi mess you up. So this would be 360 over pi degrees, because again our radianness canceled and we're just left with the degrees. And I certainly wouldn't argue that this is a horrible looking value. We could find some decimal approximation for it if we wanted something nicer. It'd be somewhere around 112 degrees or something. I'm going to say ish. I don't exactly know. It might be closer to 100. I don't know. Somewhere around there. Maybe 113. It doesn't matter. Somewhere around there. But this is a degree measure with a pi in it. If we need an exact value, leave the pi there. If we want a decimal approximation, do the division. Get a decimal approximation. So, again, on your notes, we've got that nice circle. We will use this circle a tremendous amount as a tool. So doing that counting your way around that I talked about before, practicing that, really helpful and important. You've got some conversions. I try not to get too tied up in thinking of these as two different formulas. They're just two versions of the same relationship. So you can do some of those conversions. We had a nice talk about coterminal angles, just again adding and subtracting full rotations. If you're in degree mode, a full rotation is 360. If you're in radian mode, we'd be adding or subtracting multiples of 2 pi, because that's what a full rotation is in radians. So, as a nice example, finding angles that are coterminal to 5 pi over 4. Add 2 pi to 5 pi over 4, get your common denominators, do all that good work, and you'll get another positive angle. You want negative angles? Subtract 2 pi, you'll get negative angles. So play around with that. The same thing with the 60s and negative 60s. Are those coterminal? If they're coterminal, their difference should be an even multiple of 360. Find out if they are. Or draw them and look at them and see whether they are or not. Arc length of a circle. We talked about that arc length of a circle. That's our s equals 2 pi. Remember, we made a mess since then, didn't we? I'm not sure I like this whiteboard tool. I might find a different one for us. Because our radian measure was defined as the ratio between the arc length and the radius, then our arc length is r times that theta. But again, only if that is in radians. If it's in degrees, it doesn't work. So make sure you're careful with that tool. Similar tool with the hands of our clock. Now, I'm going to make another video about the area of a sector and linear and angular speed, because that takes some talking about. I'll post that shortly. But as usual, if you have any questions about this, let me know and we'll go through it. Until then, I hope you have a wonderful day.